How to make the diagnosis of soil structure quality and compaction with the STRUDEL method. Here we'll show you how to take a sample, do volume measurements, do a visual evaluation of soil structure in the lab, and how to calculate the different physical parameters. And now, what's the material for sampling? A box, a spade, a trowel, a measuring meter, a knife, always useful, cylinders, plastic bags for the cylinders, outside plastic bags, pencil and some paper, permanent marker, the sampler, and a hammer. So now I want to sample from 5 to 10 centimeters, so this means that I will take away the 5 first centimeters of the soil and insert the plastic bag inside, that it's a few centimeters further, so you can take it away. Once it's in, you have to screw it together. During sampling, you have to pay attention that the cylinder goes straight into the soil and it doesn't zigzag. So if you want to take several samples, it's best to hammer them all in and extract them at the end so you don't destruct the structure by sampling. Of course, you can also take a sample inside a soil profile. There are 2 ways of getting your sampler out. First, with a knife, scratch all around it and extract it. Or you turn it aside and you have to just push the sample down on the same time. To extract the sample, you have to push with your whole hand to gentle with the structure and pull on the plastic bag inside and outside of the cylinder and then slowly drag the sample like that. So you can twist the plastic, put a little name, and put it in a second plastic bag, which will be nicely closed so that you can get the water content during sampling and will protect it against drying. If you don't have all this material, you can just take a spade, a knife, and take an undisturbed sample just by digging out a clod. I'll cut off the first 4 to 5 centimeters. The clod sample should be slightly bigger than what you planned because you can cut it right in the lab. During transportation, soil structure must be preserved too. So either you fill a box with bubble wrap or you can fill it with crumbly soil. So you put the samples in the box and close the lid. So once the sample arrives in the lab, you have to prepare them, meaning cut them on a straight surface so that they can equilibrate on the desorption plate. The samples must equilibrate at a matrix potential of -100 hectopascal. So the easiest is to start by a humectation to -10 hectopascal, and after a week let them desorb for another week at -100. Once the samples are equilibrated at -100 hectopascal, you have to measure the weight and the volume. We're going to measure the volume with the plastic bag method. What you need is a scale, something to stabilize the sample, a bucket of water, a vacuum pump, plastic bags, something to close the plastic bag, scissors, a cloth, because that's very useful, and something to write. Should introduce the sample in the plastic bag and close hermetically around the tube in order to create vacuum. We'll create vacuum with a differential pressure of -400 hectopascal. To get the volume of the sample, we use Archimedes' principle and measure the mass of the volume of water displaced by the sample. And now we cut the plastic bag and measure the quantity of plastic that has been immersed in water. A volume measurement must be taken at least twice to be sure of the measure, and there shouldn't be a higher difference than 1 cubic centimeter between the 2 measurements. It must be repeated as much as necessary in order to get in this 1 cubic centimeter range. One of the advantages of this method is that the plastic bag takes the shape of the sample, even for samples that had a little problem during sampling like this one. 3 things to pay attention to. First, nothing should touch the scale or the bucket. Beware of the tube and beware of the plastic bag. 2, don't forget to do the Tara. And third, be aware of bubbles that could be trapped in the plastic bag during measurement. One little tip to avoid the bubbles is to slightly shake the sample during measurement, and that will free the little bubbles that could be trapped in the plastic bag. So this is how a sample looks like when an earthworm has been captured inside it. If we measure and evaluate the soil structure, it will not be the soil structure of the field, but a soil structure that has been created by the earthworm that moved around during 1 month in 150 cubic centimeter soil. With CORVES, you can evaluate the soil structure quality of a sample in lab conditions. As for field VES, you use an illustrated chart with scores from 1 to 5. 1 being a very good structure and 5 a very bad structure. Compared to a field evaluation, it will take much more time, but it has 2 major advantages. First, all samples are equilibrated at -100 hectopascal, so this means that they are more comparable. Second, the samples are anonymous and out of context, which makes the evaluation a little more objective. We observe 3 criteria: aggregate shape, porosity, and breaking difficulty. To avoid subjectivity, it's best to be 2 for the evaluation. After CORVES evaluation, it can be useful to crumble the sample in order to make sieving easier. The water content and air content are reported to the dry mass of the soil. Therefore, the sample must be dried at 105 degrees until the mass is constant. Of course, this mass must be weighed at the end. Because we need to remove the volume and the mass of stones, we need to sieve, and then we can use the fine fraction for further analysis. And that was the lab part. So now we've got the mass at -100 hectopascal, the volume at -100 hectopascal, the mass of soil dried at 105 degrees. All of that needs to be reported to the fine fraction, so you have to retrieve the volume and the mass of the coarse fraction. So this means that the mass of the sample at -100 hectopascal is the mass that you measured minus the mass of the stones, and the mass of the dry soil is also the mass that you measured minus the mass of the stones. With that, we'll calculate the water content at -100 hectopascal, which is simply the mass at -100 minus the dry mass. Because it's the gravimetric water content, we'll divide it by the dry mass, and we'll get gram of water per gram of dry soil. With all that, we can measure the specific volume at -100 hectopascal, which is simply the volume as we measured with the plastic bag minus the volume of the stones. All that divided by the dry mass, and we'll end up with cubic centimeters per gram of dry soil. And to get the bulk density, we'll just do the inverse of the volume, and that will give us grams per cubic centimeters. To calculate the air content, you simply can imagine a soil sample. The sample has a certain volume, which is separated in 3 phases: a volume of air, a volume of water, and a volume of solid, which is mainly fine earth, and of course there are some stones. But we took care of these stones and have removed them. To calculate the gravimetric air content, you simply take the specific volume minus the water content minus the specific volume of the particles, which is 1 on the real density of particles, usually estimated at 2.65 gram per cubic centimeters. With all that, we'll get cubic centimeters of air per gram of dry soil. These 4 parameters will enable a good characterization for soil structure quality. To distinguish a good structure from a bad structure, we even have reference values which have been developed in particular for gravimetric air content. Now you know how to do a precise diagnosis of soil structure quality. All that is left is to watch the video on visual evaluations in the field.